All right, up to this point, what has this chapter taught us? What did you learn?
Counting electrons.
Counting electrons. Not this chapter, though. That was last chapter.
For the homework.
Oh, yes, for the homework. But this chapter. What did we learn? What? Oh, how to balance equations. All right, that's a biggie for this chapter. All right, what is the principle that guides why we have to balance equations? It's a law. What law goes with balancing equations? Conservation of mass. Okay. The conservation of mass means that at the beginning of a chemical reaction, we must have the exact same amount of mass at the end of the reaction. All right. And so things are neither created nor are they destroyed in a chemical reaction. Now, you may have heard something different in physics, where there is a law of the of mass and energy conservation. In physics, there are ways in which we can convert mass directly into energy, governed by this equation: E equals mc squared. Some people know this one. Who did this one? Albert Einstein. Okay, where mass times the speed of light squared. But we can't ever get that way in a chemical reaction. So the law of conservation of mass is as far as we have to take it in chemistry, because we will never convert any mass into energy directly. So we will conserve our mass. That means we have to actually count how many things are at the beginning, how many things are at the end. It must be balanced for anything to be meaningful. Now, a chemical reaction, remember, is a chemical story, and it starts with what? What do we call the things that we start with in a chemical reaction? The reactants. And then at the end we have the products. What indicates that we've done something chemical? In our chemical equation, it's the what? It's the combination of the arrow and the products at the end. Now you can have reactants and an arrow and something that says NR. What does that tell us? No reaction occurred. Okay. And so you can mix things together and absolutely no reactions actually occurs. They're not very interesting to us. We don't see it very often, but that actually happens. All right. And we have numbers that are in a chemical equation. We define them, subscripts and coefficients. Which one can we change when we balance equations, subscripts or coefficients? Coefficients. Okay. All right. We then went, and the next concept that was big on this list was predicting products. Can you remember any equation that you have to predict the product for? What is it? Combustion. And it's the combustion of what? Of a hydrocarbon. So hydrocarbon combust. Okay, produces what? Water, good. And CO2 gas. Okay. What is a hydrocarbon? A compound that has what? Was it hydrogen, carbon, or hydrogen, carbon, and what? Oxygen. They have those elements. It can be considered a hydrocarbon. Okay. What other things that we needed to predict? A metal plus what? Water produces a metal hydroxide plus hydrogen gas. Okay, that's another one that we can predict. Now, the metals that are available to do this, does every metal do this? No, only two groups do. Which two? Group 1 and 2, or the alkaline earth metals and the alkali metals. There are two in which I'd like you to be able to classify: decomposition and combination. What is the difference between decomposition and combination? Simple. Decomposition, you get more at the end than what you started with. Something fell apart. Combination, you have less at the end because things came together. Okay. The last is that you have to predict is metathesis reaction. What's a metathesis reaction? High school, you might have learned double displacement. The ions switch. So A cation X anion plus B cation Y anion become what? A what? AY plus BX. Now there has to be a what's called driving force. It's the force. Okay. What causes these things to happen? There are three things. I can form three things that would actually make this go. That means over here, one of these two have to be, okay, a solid or precipitate. Okay? Or I have to form a gas. Gases that you know. All the diatomic gases, oxygen, nitrogen, okay, hydrogen, CO2 is a gas. H2S was a really stinky gas that you're going to learn in lab, okay? And so there are a few gases, but if you actually form a gas, you drive this reaction, make it go, and the last is forming a liquid, which is a non-electrolyte or a weak electrolyte, and most of the time, the only liquid that you'll form is water. Every so often you might form mercury, okay, but that is a liquid. And then we will get into something, not this chapter, but a little bit later, what's called weak acid might be the driving force where you create a weak acid, but that's a little bit more complex. We'll get to that in a moment. Most of it, what you'll see is solid, which we call a precipitate, a gas, or liquid, which is water. All right, so that's what we know up to this point in time. Now we're going to learn a couple more things. All right, so predicting products basically is some memorization about what might happen. Balancing equations, you have to have a strategy. Okay, what did I tell you to do when you balanced equations? Balance what? One single element at a time. What do you try to leave last? Oxygen and hydrogen second to last. And that's not always the case, but most of the time you leave those last, especially in the more complex. Here's the reason. The reason why you leave oxygen last is because oxygen sometimes ends up in two places in the end. And so in the products, if you have two different places, then the distribution can be really weird. So if you have one, well, maybe the other one should have been the one that raised, and so it's very hard to drive having two starting points. If you start on one side with one element, that's a much easier time, and usually the oxygens will work out in the end, or it will be a very simple calculation at the end. What happens when you finally get to everything and you can't work it out? Okay, what you do is you identify the atom that has the highest on either the products or the reactant side. Usually when you've done that, you pick the first compound or element and you work from that one. What you have done is you've assumed that there was one there when you made that decision. Okay? And so you made all of your decisions based upon you had one of those and it didn't work out. You go back to the first one that you worked from and you put a 2 in front of it. Maybe 2 of those is what you need to start with. And if 2 doesn't work, 3 might work. And if 3 doesn't work, 4 might work. And 5 doesn't work, you start to think about maybe there's something wrong. Okay? You shouldn't go very, very high. All right? If you get into 11, you're done for. Okay? Key to this, is this something you want to do in pen? Not necessarily. Chemistry is not, this whole chapter is not a pen chapter. This whole chapter is a pencil chapter. Okay? And so, all right. Now, balancing equations was one concept, right? Well, take a look at this. You have 2 homework assignments, okay, for this chapter. Here is the first. And what do you see the questions here? What are you going to do? Balance equations for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh my goodness. All 20 of them are balancing. We're going to give you lots of practice on balancing. Why do you think we give you lots of practice on balancing? It may be on the exam. It may be important. And it will be important for us to solve things later in this chapter. Okay? It can be a question in and of itself, right? All by itself, balance an equation. And I didn't even ask you to predict a product on these. I gave you the product. But that's not the kind of question I like to ask, really, is it? I like to ask one of those questions in which you have to do like all the steps to finally get to the final answer. And so, but I want you to be able to balance equations. Oh my goodness, I give you names and you have to convert them into compounds. Oh my goodness, that's last chapter. It will never go away, okay? And this is great practice because now you're practicing for the final, right? Because you have to keep those skill sets. We're going to let you practice a little bit from last chapter. So I would expect that before the break, you should be able to get all these done because we're going to get into more complex things. Not that it is any harder, but we're going to learn types of problems that require you to learn different steps. Okay. All right, I want to warn you. If you are going and we're working on Lewis structures, here's the wrong way to do it. Looking at the structure and drawing lines. That's not your first step. What is the first step when you approach drawing Lewis structures? Count the electrons. Okay? If you start drawing lines, you're wrong. Okay? Now here's the problem. You start drawing lines, you'll be right about 60% of the time, maybe 70% of the time. If you're good with 60% of the time, go for it. Okay? But if you want 100%, start by counting electrons. All right. Okay. So let's go to this next example. And here is a reaction that I'm going to give to you. And I don't exactly tell you everything. It's not as easy in terms of seeing it on a piece of paper written out as an equation, but the surface of aluminum metal undergoes a combination reaction with oxygen in the air. Okay? And so, I tell you it's a combination. I tell you the 2 things. How would I represent aluminum metal? What would you write? AL, good. Whew. And then what would it be? Would it be a solid, liquid, or gas? Solid. That's the element, the metal, aluminum. All right, how do I write oxygen? You have to write O2 because it's diatomic. And is it a solid, liquid? It is a gas. Okay. Oh boy. I said combination. So when these 2 things react, they will form a compound. All right, this is where you need to work a little bit scratch on the piece of paper and not write it at the end because you're going to confuse yourself. But I know you're not going to follow this, but I'm going to tell you it anyway. Right over in somewhere else, Aluminum. When aluminum reacts, what charge does it become? A 3 plus. And when oxygen reacts, what charge does it become? 2 minus. Does a plus 3 and a 2 minus create a good compound that is neutral? Nope, crisscross. The compound is aluminum 2, oxygen 3. Okay? I don't get any of this confused by doing it up in my equation. Lots of numbers going to be roaming around, and you want to keep that separate. Now, what do you see? Okay, very quickly, I tell you to do oxygen last, but in a very simple one, you're going to see a problem with oxygen. What do you see the problem with oxygen between the reactants and the products? One is what and one is what? One is even and the other is what? Odd. Could I ever make the even one odd? No. So what is the quickest way to make the product side even? Put a 2 coefficient in front. That makes how many oxygens? 6, correct? And then how do I make 6 on the reactant side? I put a 3 in front. Am I done? No. Aluminium, as they say in Britain. How many do I need over in the reactant side? 4. Ooh, you've done it. Okay, next. All right, I don't like this question. I would not give this to you on the test, but a decomposition reaction occurs when a solid barium carbonate is heated. It forms 2 products, a solid compound and a gas compound. Oh, good night. All right, scratch a piece of paper. What is barium? What's its elemental symbol? Ba. What charge does it have? What did you have? A plus 2. Carbonate. CO what? 3. What charge? 2 negative. Do they come together and form a compound that is balanced? Yeah. So BaCO3. Now here's where you don't really have a lot of information. All right? Can anybody guess what gas might jump out of that? It would be carbon dioxide. Carbon dioxide can fall out. That is a gas. We were told this was a solid. Plus whatever is left over, barium and oxide. All right? Barium is a plus 2 charge. Oxygen is a what charge? Minus 2. That would be a compound. And in this case, most likely, it's going to be still a solid because it tells us it's going to make a solid. And when I look at this, I have 1 barium on one side, 1 barium on the other, correct? 1 carbon on one side, 1 carbon on the other, correct? 3 oxygens in the reactant side, and how many in the products? 3. I am balanced. You actually might end up with a question where once you make the compound, it is balanced. Don't overthink it. Don't start throwing in numbers. It can be that way. Okay? And so, balancing equations. Again, remember, I could spend 50 minutes and balance equations. I could spend 50 minutes and juggle. Doesn't mean that you can juggle at the end. You're going to have to try to do some of these. Now, I didn't make you predict on that first assignment, but you should be able to approach these. Here's where you're going to run into trouble in those questions. Usually the first ones where they give you the compounds on both sides, you should be able to get those. That shouldn't bring too many problems. You might have to start over once or twice with some of them, but you should get there. This is where you get problems, when they give you the names and the names. If you do not create the correct compounds with the correct subscripts, they may never balance. And so if you go too many times, always go back and make sure that your compounds were formed correctly, because that's where the mistake usually lies when you do that. Okay? All right. What kind of math do you have to use with balancing equations? You've got to add, you have to subtract, and you have to multiply. Okay? Got it? Too hard? Got your iPhones. Come on now. Should be able to get that done, right? Okay. Next concept, the mole. Oh my goodness. Some people like the mole, some people hate the mole, some people have no idea what the mole is. They've just heard moles. Okay. Why in the world do we have to go to something called a mole? Let me go back just one step. In this example, on this equation, it says that 1 barium carbonate will produce 1 CO2 and 1 barium oxide. Okay? The ratio is 1 to 1 to 1. All right? And that's fine. But the problem is, the molecules are so small, can you see one? If you have a microscope, can you see one? No. If you have a very powerful microscope, can you see one? No. You actually have to have a microscope that's called a electron microscope. It costs way too much money, and you actually have to have a person that is hired full-time just to run it. You can actually see one. It's very hard. It costs a lot of money, but you cannot see them. And so, we don't ever go into the lab and ask you to react one molecule with one molecule, even though it has to be 1 to 1 at a certain point in time. So we have to measure out enough for you to actually physically hold in your hand, well, not hold in your hand, but put on a beaker, put in a test tube to actually do a reaction. When you do that, you put trillions times trillions times trillions of molecules in that test tube, enough so that you can see. And so we have to think about these molecules reacting 1 to 1, but in large numbers. And so we're going to make up a really large number that is proportionate to. And so the mole is that number. Now, when people make things, we kind of do this already. We kind of group things. And so when you go to Dunkin' Donuts, you can buy a donut by the dozen, right? And so that seems to be a reasonable, although I would argue, amount of donuts to buy, a dozen. And you buy them by the dozen. But when the bakers make donuts, they do it in a different pattern. They do not make a dozen. They make a baker's dozen. What is a baker's dozen? 13. Why do they make a baker's dozen? They have to. They know they're going to sell it in dozens, so they make one extra if it falls on the ground, so they don't put it back and sell it to you. Or if they do it perfect, they get one for themselves. Okay? But they think in units and in groups. Okay? There's another group that you may or may not know, a gross. Do you know what a gross is of something? It is a dozen dozens, or 144. When you start to make lots of things, you can buy them by the gross. All right? These are just made-up numbers, and they're made-up conversion factors. 1 dozen is 12 things. 1 gross is 144. It's just a made-up conversion factor, just like the butts. 126 gallons is 1 butts. Who made that? I have no idea. But they just defined this. And so we're going to define a number. 1 mole is, Avogadro is given the credit for this, 6.022 times 10 to the 23rd things. Okay? And so it is just like a dozen, it's a number. And so if I had 1 mole of carbon-12 atoms, I'll have 6.02 times 10 to the 23rd. Or if I had 1 mole of water atoms, I have 6.02 times 10 to the 23rd. If I have 1 mole of M&Ms. Now here's the deal. If I took M&Ms, and this is the plain M&M, not the mini, not the peanut, not the peanut butter, but just regular M&Ms, and I poured 1 mole of M&Ms over the ground, And I start in Florida, and I pour them all the way up to Maine, and I pour them all the way over to Washington State, all the way down California, all the way through Texas and back to Florida, and I fill up the entire United States with 1 mole of M&Ms. Do you know how thick in miles 1 mole would take of M&Ms?
1 deep.
Deep, over the entire continental U.S. About 20 miles. That is 1 mole of M&Ms. Okay? I could also then go into the lab for about, you pour 20 mils, right? In your lab. You take out 2 mils, only 18 mils. Do you know how small that was? Okay? That is 1 mole of water. We work with really, really tiny things, but a whole lot of them. And so we have to have something that converts, okay? Because what ultimately we have to do is we have to account for every 1 atom reacting with 1 atom to create 1 product. We just do them with a large number. This is actually, if you measured it out, 60 quadrillion things, whatever they are, okay? And anything can be a mole. Now, what is great about the mole is this, and this is one of the things that Avogadro determined. 1 molecule of carbon weighs 12 AMUs, atomic mass units. We never measure that. That's kind of an oddball number. This is what we do. If I want to measure out 6.022 times 10 to the 23rd carbon atoms, I don't count them. You would spend forever counting them. But you can do this. You can weigh 12 grams, and if it's exactly 12 grams on the balance, that represents 6.022 times 10 to the 23rd carbon atoms. For water, if I measure out 18.02 grams, it would be equal to 1 mole. For nitrate, it would be 62.01 grams for every 1 mole. Okay? And so we are going to do, and we're going to create what are called formula weights or molar masses. The term is the same. If you hear formula weight or molar mass, exactly the same. All right. For your problems, we're going to need these molecular weights or molar masses, okay? But this is where you get them. You get them from the periodic chart, okay? And so if I wanted to know how much barium carbonate, remember that compound? This is what I would do. I would punch on barium. Barium. Okay. That's what barium weighs. 137. Oh, no, that was 2 bariums. I hit it twice. Let's restart. Restart. Okay, barium once. Okay. Carbonate. C. Okay. O. And 3. And it didn't show, but it's highlighted. It could be an issue with the iPad. I would have to weigh out 197.336 grams to get to that. All right. Let me show you one other. What if you had something like aluminum sulfate, aluminum sulfate? Okay. How in the world would that look? You can't put parentheses in this thing. So what you would do is aluminum, 2. Then you would have how many sulfurs? 3. You would have to put it in this way. Sulfur, 3. Oh, I have no idea what I selected. aluminum 3, sulfur, it was aluminum 2, wasn't it? Good night. Aluminum 2, sulfur 3. How many oxygens? 12. And then O, 1, 2. And so you have to distribute this to use this tool. It looks weird, and it looks even weirder on the iPad than it will on your computer. And so aluminum 2, sulfur 3, oxygen 12 to get the correct. And if you don't use this calculation, CHEM-111 will not count you right. Okay? You can go to the periodic table and do all of this, and you'll get something very close. But is CHEM-111 wanting close? No, CHEM-111 wants perfection, and it defines perfection as itself. You may know a person just like that. Okay? So if you need to actually calculate it, and you're going to need to practice it by yourself because on the exam you won't have CHEM-111. You will be given the name or formula of the compound. To predict the formula if given the name, multiply the number of subscripts by the mass in the periodic table, round after 2 decimal places, and you add them all up. The units will be grams per mole. So an example, ammonium sulfate. There are 2 nitrogens. You multiply it by 14.01. Hydrogen, there are 8 of those. 1 sulfur and 4 oxygens will total up an amount. And then you will round it to 2 decimal places. All right. On the exam, we're much more lenient in terms of your own calculation than what CHEM-111 will be. And in the multiple choice, select the closest one. All right. If I do this one carbon, 12H22O11, do you know what that is? Carbon 12H22O11? You may have seen a formula like this before. If you classify it as what? It fits into what classification that I taught you today? What kind of compound? Hydrocarbon. In particular, this is a sugar, and even more specifically, this is table sugar. Okay. To calculate carbon, 12 times 12.01. Hydrogen, I have 22 times 1.01. And oxygen, I have 11 times, 16. Nope, let me go back. I'll erase it. It would be oxygen, I have 11 of them times 16.00. And so, stop. 12.01 times 12 is 144. 22 times 1.01. All right, so if you want to eat 1 mole of table sugar, you have to eat 342.34 grams to eat 1 mole of table sugar, or a dozen donuts. No, but that's a lot. All right. And so, what does molar mass do for me? Okay, it is a conversion factor that you get to calculate. Okay, that's it. For the most part, it is going to be used as a conversion factor. And at this point in time, you have 2 conversion factors. Okay, you have simply 1 mole is this number of things, okay, things, and that could be atoms, that could be molecules, that could be M&Ms. That's one conversion factor, and then the molar mass is the grams needed to make 1 mole, and that is for every compound. So, if you have conversion factors, I'm going to then make you do what? Make you convert. Okay? And remember, a conversion factor can be grams over moles or moles over grams. What makes you decide which way to use it? What you're given. Because you have to cancel out a unit, converting into another unit. And you can have the number of things over 1 mole or 1 mole over the number of things. And so here is the transition that you can transition between grams to moles and moles to molecules, and you can go back and forth. Also, you can use molar mass. That's another terminology. It doesn't have to be formula weight. It can be molar mass. And so, going from grams to moles and moles to molecules. This one is probably the one you're going to use a lot more often, converting grams into moles. Okay, going to molecules sometimes. In real life, very few times do you ever go to number of molecules, but on like CHEM-111 questions, lots of times you'll go to those types of things. So examples of very simple, non-CHEM-111 type of problems. How many moles are in just a certain amount of this compound? What's that compound's name? Sodium. The old name is sodium bicarbonate. Okay. The new name is sodium hydrogen carbonate. Okay. And so if I had 532 grams inside a jar, then where did I get this? Did I just make that up? No, you calculated it. You think I just made it up. Okay, you calculated it from, if it is on the test, you calculate it from a periodic table. If it is in CHEM-111, you calculate it exclusively using that tool. And so, in this case, grams cancel out, moles are left. How many grams are in C6H12O6? Okay, this is not very many grams, or not very many moles, minus 2 moles. Okay, 1 mole of C6H12O6. Oh, good night. All right, so 12.01 times 6 of them is 72.06 for carbon. 12 times 1.01 is 12.12 for hydrogen. And 6 times 16 is 96 for oxygen, plus 12.12 plus 72.06 is 180.18 grams of C6H12O6. In this case, I will have grams of C6H12O6, and if I do that times 0.02989, I get 5 grams, and in this case I have 4 sig figs, 386 grams. Okay, so grams to moles, moles to grams. And then how many molecules are in 4.2 grams? Can't go from grams directly into molecules, but I can go from grams to moles, because I'll cancel out grams, and then moles to number of molecules, and I can calculate how many molecules I have in that small amount. All right. Okay. go ahead and pull out a piece of paper and tell me how many atoms of aluminum are in 3.45 grams of aluminum carbonate. There's going to be one more step. You're going to need one more conversion factor to solve this problem. But you should have enough information to identify what that piece of information you need. Here, let me start you off. 3.45 grams. Okay. And how do I make that compound? Al and carbonate, CO3, 3 plus, 2 minus. That should be helpful. Okay. I circled the tricky part. Starting off with grams, you can change grams into moles of the compound. Here's the tricky part. I didn't want the whole compound, I only wanted aluminum. There is a conversion factor that you can derive from the equation, and it says for every one of the compound, you're looking at it, I have 2 aluminums. Okay? And then I would tell how many aluminum, moles of aluminum I have, and then I convert moles of aluminum to atoms of aluminum. Okay? You could have converted moles of the whole compound into atoms of the whole compound and then do the conversion of the whole compound. There, for every one compound there is 2 aluminums. Mathematically that's the same in the same logic, but that was one more conversion factor. You can derive a conversion factor from the compound formula itself. Okay, there's a relationship that you can see there.